Yeah, if everybody on Zoom could mute yourself, so we're not getting any stray audio. Yeah, it looks like we have good attendance both in here and on Zoom. So we all know Anne. So I won't go into too much of an introduction, except she's going to tell us about her newly accepted paper. So take it away, Anne.
Okay, I just got the page proofs for this paper, and if any of you have had experience with the new method, you know it stinks. Doing page proofs this way needs improvement. Anyway, it will be accepted soon. So we have a collection of 1 solar mass stars as on the main sequence. And I can't make this go forward.
Right. Clicking on it and then.
Well, so much for that.
Maybe on the actual slide.
Okay. So just for your entertainment, here is regular lithium, beryllium, and boron in the flesh. Little sample. And they are very important elements, particularly lithium and beryllium, because they give us clues as to what's going on inside the star, and there's not very many of those. We look at what's on the surface, and we use them as probes to see what's happening inside. So this little model shows that black circle is the outer convection zone of a standard 1 solar mass star. Inside the red circle, there's no more lithium because it's destroyed at 2.5 million degrees. Inside the blue circle, if any beryllium atoms get down that deep, they're gone too. But it has to get all the way down to the purple circle for a boron atom to get destroyed by thermonuclear reactions. So this is a spectrum, an good old-fashioned photographic spectrum of the sun. This is work done by Greenstein and Tanbrecht Hansen, 1954. You can see, I hope, the 2 lines there that are labeled 3 and 4. Those are beryllium, actual beryllium lines. And to the left, sort of all by itself there, 3129, is a line of ionized vanadium. Now I'm going to show you a modern spectrum like that. I'm sorry, I messed that up. It's ionized zirconium. Vanadium is the other one. So that line all by itself was zirconium, and then you see the 2 beryllium lines I have with little red arrows. But somehow the red arrows are not lined up. Well, forget the red arrows, they are labeled as BE Roman numeral 2 for those 2 lines. Now, by contrast, this is the lithium region. So you see beryllium, this is 8 angstroms in beryllium region, and it has an enormous number of lines messing up the spectrum. Whereas lithium is easy. There's a lithium doublet there. This is similarly 8 angstroms, and just a few iron lines to also be modeled. So what we did was take a sample of 1,581 stars that were observed for lithium. I told you lithium is easy. These were F, G, and K stars, and we selected the G stars from this sample, G stars being solar stars, on the basis of these temperatures that were the parameters that were determined so uniformly by this group. So we found solar temperatures, solar surface gravity, solar metallicity. Solar mass was one of our key parameters, key criteria, and age. So this is luminosity, log G versus temperature, showing the distribution of the stars we observed. These were all observed at Keck with high-res spectrograph and high dispersion and high signal to noise. This was done over 12 different observing nights and 4 different observing runs. We squeezed in these bright stars. So this is the lithium observations of the stars that we observe for beryllium. And these are organized first by their effective temperature. And there's that little yellow circle with the X through it. That's a position of the sun and its temperature and its lithium abundance. And the next panel shows the distribution of mass. You see, we really tried to have them be within 2% of the solar mass. And the third panel is for their age. So most of our sample is a little bit older than the sun, but we tried to have them as close to the sun as we could. So this is a sample of the beryllium spectra in 4 of these stars. I have labeled the beryllium lines there in red. So you see that they stand out, but it is a rather crowded region in the spectrum. And in the lower right, you'll see that the lines are a little fatter. And that's because that particular star is rotating a little bit, and all the lines are broader due to that rotation. And I wouldn't want to go to stars rotating much more rapidly than that to try to extract the beryllium abundance. So here is the actual beryllium abundances for 2 of the stars. We do this with spectral synthesis. In this diagram, the little black squares are the observed points in the spectrum. The blue line is the best fit through all of those lines. And where the 2 beryllium lines are, you see red dotted lines that are a factor of 2 higher, a factor of 2 lower. Plus, there's a little red dotted line that is with no beryllium at all. So we can determine beryllium abundances for all 52 of our stars by this method. So this is a fun thing that happened. We found 2 stars with absolutely no beryllium at all. But we found their companions. I mean, these are virtually identical in their spectra. One of those stars has beryllium, the one with the dashed black line, nice strong beryllium line, and the ones with the red have nothing. And there were two different stars with no beryllium, and we found 2 exact matches in their spectrum. And we figured out that it must be that those 2 stars with no beryllium are a product either of mass transfer with another star or a merger with another star, and that messes up the outer regions of that star so that they all get mixed up, and lithium and beryllium both get down to the level where they're destroyed. So here's the results for beryllium. On the left, we show beryllium with mass. And you see down below those two stars that have just upper limits on the beryllium. But most of the stars are clumped up at the top, nearly the same amount of beryllium as each other. There's an error bar down in the lower right, lower left. So the range there isn't much beyond the error range. We show a plot with temperature. The vertical lines here are representing the solar temperature and the solar mass. The horizontal lines are representing the solar system amount of beryllium. Now, if we look at metallicity and age, for both of those, we see a slight trend of beryllium increasing with increasing metallicity and beryllium increasing with increasing age. And presumably this is due to the production of beryllium during the lifetime of the galaxy, primarily by energetic protons and neutrons, like 150 MeV, that bang into a carbon or nitrogen, oxygen nucleus floating around in the interstellar gas. And with that kind of energy, they can break up those nuclei into little pieces. And the little pieces are lithium, beryllium, boron, hydrogen, whatever. So this is going on during the life of the galaxy. So there is an increasing, slowly increasing amount of lithium, beryllium, and boron. Now we put them both together. So the next slides are going to show lithium and beryllium on the same scale and normalized to the solar system abundances. So the horizontal line there at 3.3 for lithium and 1 almost 4 for beryllium. That is the solar system abundance. We got a solar spectrum of the daytime sky for beryllium. And so that yellow dot up there with the beryllium is our result for the sun, beryllium. And down below the yellow dot circled in red with the red points is a similar, but not ours, result for the sun. So what you see is this huge spread in lithium and not much spread in beryllium, except for our two little points that have no beryllium and just have those upper limits. So you can see it's a fairly narrow mass range. Almost all the points are between those vertical lines with from 0.98 to 1.02 times the solar mass. Now we have lithium and beryllium versus temperature. So we do see a large decline with temperature for lithium. Beryllium is quite well behaved, but lithium is going down with decreasing temperature. And the amount that it's going down is more than it's accounted for by just increasing depth of the convection zone. There's some kind of extra mixing.
The two stars that don't have beryllium, where are they in the lithium? Because one of them is also a non-detection. Do both of them also have a non-detection in lithium?
I'm not responsible for the lithium result. Remember that.
Oh, okay. That's
One of them does have an upper limit. The other one has a very low detection, which I don't believe. But yeah, so you can see on this the two beryllium ones, the blue squares. And if you look down, you see for that one, there's an upper limit. Other one, I don't remember which point is that. If we look at these results versus iron, so there is a trend with increasing iron that there is less lithium, but beryllium is up there just steady and steady. And lithium and beryllium with age, you see quite a trend with age. The older stars have had more time and have been able to deplete more lithium. That's not the whole story. So here we have a range of over 600 in the amount of lithium in these stars. In beryllium, there's maybe a range of 3. And from all kinds of other work, we know that this isn't due to mass loss, it's not due to microscopic diffusion, it's not due to meridional circulation, it's not due to gravity waves. And the theory is that it's due to rotationally induced mixing caused by turbulence. And here's some of the understanding of that. Okay, there's surface rotation, and that declines with time. We have, that was known by Kraft, big study in 1967. So we have a rapidly rotating interior of these stars, and that's connected with a co-rotating that's driven by magnetism, the co-rotating wind. And so the surface layers then start to spin down. These are according to the prescription of Endel and Sophia. So this convective envelope is losing angular momentum by this stellar wind. So this creates a velocity, angular velocity gradient between the interior and the surface. And that gradient causes a shear instability there, which redistributes the matter. I mean, forget about all the other things that's redistributed. The matter gets redistributed, so some of those light elements get distributed deeper into the star. And if they get to their critical temperature, poof. For lithium, just paying no mind, sees a proton and poof, it becomes 2 helium atoms. Very fragile when the temperature becomes 2.5 million degrees. So we can look at the models. Now, these are models that were developed in 1997. And the details of the numbers of these models aren't published. So I've had to kind of extract them from another paper. So I have extracted them as a function of temperature for stars that are 1.7 gigayears, so quite a bit younger than the sun. And the dashed line, the upper one, is a star that starts life rotating at 10 kilometers a second. The lower one starts life at 30 kilometers a second and spins down more and loses more beryllium. So it is mostly. However, for one solar mass stars, these models predict a slope for one solar mass stars between lithium and beryllium to be 0.2. And I've tried to draw that, what a slope of 0.2 would be in that blue line in the left-hand thing there at the bottom, which is no match for our stars there that are closest to the sun in temperature. There's no slope between lithium and beryllium because there's no change in the beryllium. And on the right-hand side, those are those few stars that are most like the sun in all those 5 parameters. Again, the slope is pretty close to 0. So there's these show that there's something wrong with the model. So with these 52 stars, we see beryllium increases slightly with age and slightly with metallicity, which is okay, we expect that. But the range is only a factor of 3 compared to this huge range in lithium, factor of 600. And then we have these neat 2 stars that have no lithium and no beryllium. And our explanation for that is that they're interacting with it again. Then the rotation models now are depleting too much beryllium. And so those models need to be revised and updated. And that's actually in progress. I have some information from Delianis and Pincinel were the authors of the study in 1997. Delianis is one of the authors on this paper. Pincinel has sent me a message how they are now working on revising this model. So we can hope there will be a better explanation of what's happening with it. So that's my latest update. Thank you.
Thank you, Anne. Questions?
Ben, I have a dumb one. You're saying that the beryllium increases with time for the stars. That's because the beryllium is actually being created on the surface of the star and
No,
from cosmic
it's
rays?
created in the interstellar medium. So the younger stars form with more beryllium than the older ones because the interstellar medium is enriched.
Well, maybe I misread your plot then, the x-axis. I took it the other way around. Okay, that clarifies things.
Okay.
Questions for Anne? Rita?
How tightly constrained are like the masses and temperatures and ages for this?
The mass determinations,
Yeah, like the masses
it's
and
typically
ages.
good to plus or minus 0.02, according to this big study by Ramirez. So that's still within, I mean, we tried to look at ones within plus or minus 0.02, but for each one of those, an error of plus or minus 0.02.
How are those able to tell?
I think primarily by isotopes. So there's a big uncertainty there.
Yeah, the Ramirez group, they're known for doing this differential solar spectroscopy measurements, and then they do superimputing to get the rest.
And they also identify whether they're thin disk or thick disk stars. All but one of them. Ours was thin disk.
Both, actually.
Go for it.
What is are the kinematic ages for the two beryllium depleted stars? Basically, is there some non-isochrone age for
I
those
don't
two?
know. I don't know. But one of them is a known binary.
But it's still in a binary, so it was a triple.
Yeah.
So you know what the other stars?
I
Obviously,
do.
less
I
mass.
mean, I know what their names are.
Oh, no, I mean, like, is it also a G star, or is it?
Oh, that one. No, I don't remember.
Yes, I have a question. I guess I'm slightly surprised that you only have these two outliers, right? Because if you have a binary interaction, I would expect this for tidal break-in to get that slowdown much faster. Can you hear me? So, like, if you have binaries and they, have tidal interactions, the star would spin down faster, right? Tidal break-in, and then you get lithium depletion faster. So I guess I'm surprised that you don't see more outliers in your plot. Does that make sense?
You're predicting that there should be more binaries in the sample,
Yeah,
and therefore more,
more outliers.
but we were purposely not selecting.
Oh, okay, so you made a cut on that. Okay.
What you see in the high resolution?
Oh,
I mean, it's somewhat technical question. So when you measure the abundances, do you take are there any non-alpha effects that you need to take into account? And you mentioned you do synthesis, so this is not line, but this is not equivalent widths, but how do you actually measure the abundance? Is it equivalent width measurements or?
no, we synthesize the whole spectrum. We have a line list of, it's over 300 lines with all of their properties, and we use this program Moog, put them all together, and it produces a spectrum. And then we make some adjustments. Sometimes we haven't corrected right for the radial velocity, sometimes the continuum, and we try to get as good a match as possible. So no, there's no equivalent width.
I have another dumb question. So, computing stellar merger rates is kind of a hot topic now. Is there some subtlety here, or can you basically just take your measurements and actually compute a stellar merger rate where the component mass is equal something like one solar mass, given your two beryllium-4 stars? Some subtlety there, or is it pretty simple to actually invert this and get a merger rate calculation?
I don't know. What did you say, Jen?
You have to be careful about rotation. If you're sitting there spinning really fast, you get extra mixing.
But these are G stars, they're not located very well.
But if they're in a binary and they're spun up,
Yeah,
then you can have a problem.
but then we selected against those.
Yes, my understanding is you already selected out all your close binary. There is no close binary in the sample, is that correct?
Except this one. And maybe the other one, but
What, close binary, or is it, how close is so this is in the beryllium 4-star depleted star, there's a companion, but how close is that companion?
I can find out. I don't know off the top of my head.
All right, if there are no more questions, let's give Dan another round of applause.